Good morning, everyone. Congratulations to everybody. This is pretty cool, and obviously we have the opportunity to share obviously knowledge, experience, and some of the thoughts that could be used for development of the future standards. So we're going to talk today about our paper, which was on reinforcement congestion in cast-in-place concrete. I believe everybody is an expert on that. Everybody has seen it. Everybody know how it looks. Everybody understand the issues, and pretty much is pretty quickly. But at the same time, we still have the same issues in the standard. So I believe that's the key of that paper, is understanding what are those challenges that we keep dealing with during the day-to-day construction. And in actually, we have a lot to do in our ACI standards to get better. So let's put it that way. It's pretty easy to understand. Let me go first. So this is our co-authors here. Initiative came from American Society of Concrete Contractors. We all are part of the Constructability Committee that we created a couple of years ago. And with the initiative from Dr. Bruce Zupernan and Jim Klinger, we were able to get led, and obviously from the industry practice, we were involved with the other co-authors, and we were able to truly help drive this initiative to get these out there in the CI article. I think it's, like I mentioned at the beginning, this is the type of things that we're talking about in this article. Again, you read it, you go through, you understand the left and right, but look at this. What do you think is this? Right? This is rebar coated with concrete. That's a structure. It's not a concrete structure. It's a rebar structure that we coated with a little bit of concrete around, right? So those are the challenges we're talking about during the day-to-day in construction. We keep getting better understanding how concrete works. We keep getting better understanding how the interface and interaction of rebar to concrete works. But we're not thinking about how we're going to have contractors build this to what we think is actually the way this should be worked. Right? Because when we draw it in paper, it looks beautiful. I can tell you the vibrator fits in the paper. But when you go to the field and try to build it all together, and you have the overlaps, you have the tolerances, you have the congestion, right? You have the horizontal and the different structures interacting with each other. You have a column and a beam, right? And then you have the slab, conduits, and you have everything. Well, look at this. How are you going to put concrete there, right? And obviously, you look a little bit of a close-up here. When you start creating openings, what happened around the openings? You have more rebar, right? And you have to create different details. Why? Because otherwise, the concrete is going to show some cracking. But at the same time, when you think about cracking and rebar, think about also, are you truly doing something by adding that much rebar there, and you believe the cracking is not going to happen because you have the rebar? Or actually you're not going to have the same amount of concrete section there that actually is going to still create a lot of cracking issues at those locations, right? So constructability becomes an issue, but then interpretation of that interaction that we believe happens, that we extrapolate from the lab to the field, is it likely even relevant? Look at that. How are you going to place concrete there? How are you going to vibrate the concrete there? Is it going to be actually all the aggregates well distributed, like you put it in your little picture in the paper, right? Is it going to look like you did it in the lab, that everything looks very beautiful and you can vibrate the concrete? Look at this. Where is the concrete going to be creating some encapsulation of that rebar there in that surface? Right? That looks beautiful. That looks amazing, right? You can make it look nicely in the paper, that you have the right amount of space, and concrete is going to go if you use a smaller aggregate. Do you think that that rebar is going to be encapsulated the way that we think it's going to be encapsulated, right? And I'm going to keep showing pictures so you can make this, you're going to get it. At some point you're going to say, Oscar, I get it. That's enough. Look at that. This is an area here that we also have some conduits. And some docks here, and we have there some bundle bars. Look at that. How are you going to be dealing with that amount of rebar congestion there? How are you going to place concrete here? This is going to almost be like a grout section. And then what happens when we build this? This is the way it looks. Doesn't matter how good you can consolidate that concrete. The concrete is not going to have the access and the ability to go and encapsulate, the rebar, and then it's not going to be able to travel to the front of that formed surface and create a nice finish. Right? So what happens then? You start creating the rework, right? Look at that guy. He's doing some rework there. And what happens when you expose people to rework? It doesn't only cost you money. It doesn't only look bad. It doesn't only create a schedule issue. What happened? You keep exposing people to areas of work that then create safety issues, right? And when we're talking about ACI 318 being a safety document, they're not thinking about the safety impacts of rework, right? And many people say, well, that's design. Well, but if you don't design correctly, it creates a construction issue. And all of a sudden, it's a different safety issue, You're likely not going to kill the people in using the structure, but you may kill a lot of people building the structure, right? Which is a different issue. Look at that. All this amount of work you have to keep doing. And the concrete look good in some areas, right? But look at how it gets on the bottom. Look at that. More rework. More rework. So again, you get the point. Congestion actually creates safety hazards, put the workers at risk, increase costs, creates rework work, and obviously adds more rework. So a few things we're going to bring here. We have only 15 minutes to give you all the message. The key, design must consider constructability. Extremely important. And we are doing a lot of efforts in the Institute to improve constructability and productivity in the codes. I'm the chair for the subcommittee on TAC for constructability and productivity. And we're working on that. We're just starting. I believe in the future we're going to get better, but we're doing some things to get better there too. Design must consider tolerances of fabrication and placement. Extremely important too. If you don't consider the way it's going to be built and how you can have and leave a space for the material to go through the rebar, you can create some issues there. Design must consider access, because if you're going to build it, you need to provide access to get to the point that you need to build the concrete, right? Otherwise, what are you doing, right? It's encapsulating something that concrete cannot flow there, then you don't create the encapsulation you assume in design. Think about what happened when you actually tried to say, well, but Oscar, you know, we just use high slump concrete. We just use ASCC. Yeah, but you didn't think about how the aggregates are going to get there, right? So it's not only thinking about using a higher slump mix, because it doesn't solve the problem most of the cases, right? Look at in this case. You don't have access to get all the material down there, right? You actually are blocking the access, and then even when you can try to vibrate that concrete a lot, what you're going to end up is segregating the concrete because you didn't account for some of the construction challenges. And in this case, and with the previous slide, is for heavy congested rebar sections. So the SCC and high slump can help, right? It can facilitate. You need to make sure to understand the mix. Have a smaller aggregate mix, right? Because that's going to be key to allow the material to move homogeneously through the section. And design must consider the section, right? The section width and the rebar congestion. And that's something we're going to start talking about here. So we have some equations that account for, you know, the location of the rebar and how much of a width you need to have. But this equation is limited, and we're providing a recommendation for adding tolerances of construction, tolerances of fabrication. And in this case, pretty much we show the example here. Constructible beam width, actually add a little bit more of that width, so you actually account for that tolerance of fabrication and placement. And then obviously consolidation by vibration. We have been in collaboration with 309, looking at the processes they have and make sure that we have it in 318. So as we're looking at that, we obviously recommending provide better access to consolidate concrete and to get the concrete closer to the placement of location. So making sure we add areas where you can actually put the pump and the concrete can get to the right place. Access is important. This is just showing an example. The left side, you can imagine that amount of rebar. How are you going to put a vibrator there? How are you going to get the vibrator? Look at that. That's pretty much driving you to go SCC immediately because you cannot vibrate the concrete. But in some cases, you can actually open some areas of work, identifying the construction, and then make sure that you can, every 5 to 10 feet, you have the port actually for the concrete to flow. Best practices of consolidation, as you see on the bottom left, this is one of the images from our paper, making sure people understand how you vibrate concrete when you have heavy congested rebar. These are best practices. You need an influence area for the vibrators to work properly. And obviously when you have a lot of rebar, how you can start spacing out that rebar congestion so you can allow those vibrators to get in. We provided also information on the radius of influence, access to consolidation and vibration insertion, so you can actually use our paper to properly evaluate, you know, how many times you need to vibrate the concrete and get an idea of effort, man hours, you know, how much access I need. Even the sequence of vibration is important. So looking at this type of table, you can start looking at more deeply in the access and the way of work. Another photo that to me is extremely interesting, you know, is realistic. It shows you the challenges we find in the field, the challenges we have to deal with to build the work, right? Making sure that we understand how we need to design the reinforcement to make sure that we get that access to vibration and make sure that information gets to 318, because we all can get out of here today knowing what is the issue and what are the solutions. But how do we communicate this to 318? And 318 considers properly how to integrate all that to their code. Right? That's extremely important that we continue to put that pressure. And then, like I said, it's not only rebar. we have other things going in that section of work that you need to actually, go around and because otherwise you would be here in a block, right? And you wouldn't have lighting, you wouldn't have water, you wouldn't have, air conditioning, right? You need to consider, everything that gets into that concrete section that eventually is used for the functionality and service of the building. And we have a reference provided that we actually provide the link provide the reference in the document. This was an industry paper that provided an example of an epidemic of rebar congestion that is seriously threatening the ability of nuclear power plant construction. And it actually gives you a point of view, of some of the challenges that we're having. It's a very good paper. It talks about recommendations to once you get to a certain congested value, in this case, 200 pounds per cubic yard is an example that they use in this case. You need to raise the flag. Pretty much, you need to raise the flag and make sure you start looking at things. However, as you start looking here, 200 may be too low of a number, because you're likely going to get into sections that actually have higher congestion. And those higher congestions are very common. We've seen it in our work. Contractors here have seen it in their work. And we need to make sure that we obviously make adequate representation of the risk, the location, the type of work, how we're going to place the concrete, and what is the most appropriate. But it's true. We have seen easily 300, 400 pounds per cubic yard of rebar in some of these sections, and we need to account for making sure we make a wise decision of how we're going to attack, right? And CRSI provide great reference information for the designer responsibility. This is also a point of view that it will be important for everybody to use and consider. And, with that, the other CRSI obviously provide very important responsibility to those design engineers. Making sure those design engineers truly are responsible for understanding the design needs, but also recognizing the placement demands, construction, and the realistic, challenges we need to face to build the work. So